Hello everyone. My name is Thomas Kim. Today is October 25th, 2023. It is 4:12 a.m. This is my Korean channel. From my Korean channel, if you click this link, you can visit my English channel. Once again, if you click this link, you can visit my Korean channel. For last few months, I have been filming videos about classical and modern physics and the differential equations. Click the playlist, scroll down, then Episode 12, Special Relativity 2. In my previous episode, I discussed proper time, proper length. Show more, download current video source code. Please select this link. Show in folder, unzip it. Rename the folder 013. Copy, paste it in your working directory. Open up Visual Studio Code. Select your working directory from folder 113. Click this button, velocity.cpp. Hit Enter. Ctrl V. I will close Welcome window. I will copy and paste these things. If you want to try my source code on your own machine, you need up-to-date C++ library extensions. I would copy and paste these things. I recently created cpp physics.hpp. In this header file, you can find constants, prefix, these classes. Also, speed of light in vacuum is defined to be c. If you put your mouse cursor, then you can read the pop-up window. Speed of light in vacuum. I will drag and drop Physics for Scientists and Engineer with Modern Physics by Survey. It is 9th edition. From this book, section 39.7. You can find example 39.7, relativistic readers of the fact. We will solve this simple problem. Then we will generalize Lorentz velocity transformation. I will arrange side by side like this. I would copy and paste Physics for Scientists and Engineers with Modern Physics by Survey 9th edition, example 39.7, relativistic leaders of the pack. Void page 1250, example 39.7a. Into main, copy the function name, paste it in function main. CPG display function name. Now I will read this example. Two motorcycle pack leaders named David and Emily are racing at relativistic speeds along perpendicular paths as shown in figure 39.15. How fast does Emily recede as seen by David over his right shoulders? I will not explain how to solve this problem, but I will implement this algorithm in generic format. So David Bx equals B 0.75 times C. By is 0. Actually, I'm typing this part. Emily Ux 0. Ui equals negative 0.90C. We have to apply these formulas. Now here, auto Bx 0.75 times C, auto By 0.0, auto Ux 0.0, auto Ui negative 0.9 times C. I implemented this algorithm like this. Auto UXP Lorentz velocity, UXP with speed, UX Vx. Here UXP stands for parallel component of UX. In the same manner, UYP stands for vertical component of U or UI. I would say U or UX. Then auto UYV Lorentz velocity UYP UX UI VX. I should have named it vertical. Right click, go to definition. This function is implemented here. I would say Lorentz velocity for UIV. This is for vertical component. Now back here, it should be UIV. UIV stands for vertical component of U or UI. Now SCD, Cout, UXP. This is parallel component. UXP, SCD, and there, copy, paste. UYV, UYV. Now open up any command prompt. CD 013. Special Relativity. Clang++, SCD, C++20. Velocity.cpp, LTBB12, OC.exe. Hit enter. CLSC. So this is our result. I would say meter per sec. Meter per sec. L. I will copy and paste. It should be CPG, 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 CPG. With this, I will divide C, C, then times C, times C. With this, we build again. CLSC. So, this is our answer. We can compare with our book. If we compare, UXP parallel component is negative 0.75C, negative 0.75C. This is vertical component, negative 0.60C. So our solution is correct. Please note that we solved this problem because this problem is very simple. David and Emily are in the XY plane. Also, David makes 90-degree angle with Emily. We could have solved this problem because this example is very simple. But in realistic applications, we can't use this approach. Instead, we have to generalize our velocity addition formula or Lorentz transform. Control-click this link, velocity addition formula. If you scroll down, we can find generalized vector operation. For transformation of velocity, we have to generalize it as explained here. I will arrange side by side like this. Scroll down. Template LCD floating point type or operator. I would use ampersand. CNA VCTR 3D type. This is U. Copy, paste. Cat is written here. I would let it be U. Actually, I am defining this operator. Now, context per or C, physics, constants, type C, speed of light in vacuum, context per or C2, C times C, or unit V, V unit. Unit V equals V over magnitude of V. This is unit vector. Or UV. This is parallel component. In this document, we are implementing this part parallel component of U, like this. U unit V, this is dot product. Then unit V, the result of dot product is scalar. Now we multiply the scalar to our unit vector, parallel to unit V, or parallel component of U in the direction V, or UV. U subtract UP, vertical component of U. So UV represent this component. Or gamma 2, we compute this part. 1 negative, not positive, negative. V dot U over C square. Now, or gamma, we compute this part. SED square root 1 minus V cross V over C square. This gamma represent this part. This gamma 2 represent this part, common denominator. Or UP, we are computing parallel component of U, like this. UP negative V over gamma 2. We computed transformation of parallel component, or UV gamma over gamma 2 times. We are computing this part, UV. Return UP plus UV. This is vector addition. Now scroll up, copy this. Scroll down, paste it here. Scroll up, it will be B. Copy, Control and paste it here. Now scroll up, we will delete this part. Instead of doing this, CNA, VCTR, 3D, V, this is parallel component, 0.0. We don't need this. Now, CNA, VCTR, 3D, U, this is 0 here. Then copy this, paste it here, semicolon. I will fix like this. Now we don't need this. We can say or U. I would say UP, then V ampersand UP. In this line, we are calling this operator function. Then we don't need this. I will simply delete SED, cout, U, meter per sec, CPG, and copy, paste, U dot C, I would say like this. Now we divide C, then times C. We rebuild CLS-C. So this is our new implementation. Our new implementation works correctly as our previous implementation. Please note that in my current implementation, I used negative here, also negative here, also negative here. Instead, if you want to implement exactly the same as in this document, then copy, paste. You can change your operator like this. Then we need positive here, also positive here. In such case, I will change it U1, 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 U1. Then copy, paste. This is U2. I will use negative B. Then vertical bar. Copy, paste. This is U2, 2, 2, 2. The result should be exactly the same. CLSC. So this result, they are the same. I will give one more line break here. Now, in some case, we don't need velocity C. I will paste it here. Now, 2 ampersand. In this case, we don't need C square here. I deleted C square. Also, I delete C square. Then scroll down, copy, paste. This is U3. I use 2 ampersand. Now we divide C. Also, we divide with C. Copy, paste. This is U3. Now U3. Copy, paste. L. We now multiply C. Then multiply C. I fixed like this. We rebuild CLSC. In all three cases, we have correct implementation. I actually implemented this operator